Hello, this is Gregory Maxwell, and in this lesson we will talk about rational functions and their graphs. Rational functions and their graphs. And of course, I'm grateful to Professor Shauna Hader of Salt Lake Community College for her PowerPoint presentations on which most of my slides in this video are based. Let's get into it right now. A rational function is a function of the form r of x equal to p of x over q of x, where p and q are polynomials. In other words, a rational function is a polynomial divided by a polynomial. Now, this is kind of like a rational number. A rational number is an integer divided by an integer as long as the denominator isn't zero. Likewise, in a rational function, you have a polynomial divided by a polynomial, and this function, the domain of this function are values for which the denominator is not zero. Let's take a look at what we mean by that. So we have a rational function with a polynomial divided by a polynomial. A polynomial has no domain restrictions. They are continuous for every real number. However, in a rational function, whenever the denominator is zero, then you are dividing by zero, and that's not allowed. So that will be a domain restriction. So to find out the domain of a rational function, simply take the denominator, which is our polynomial, set it equal to 0, and solve for x. And whatever real number values give you 0 for the denominator, then you have a domain restriction. The domain cannot include that value. So here's a quick example here. We have 5x squared divided by 3 plus x. To find the domain, we simply set 3 plus x equal to 0 and solve for x, and we realize that x equal to -3. So we say then that x cannot be -3. Any other real number will work except for -3. If we take a look at this example here, we have x minus 3 over x plus 2 times x minus 2. If you set the denominator equal to 0, you'll get x is equal to positive or -2. So we're saying that the domain is everything except for those two x values. It's all real numbers x such that x is not -2 and x is not equal to 2. And here's another example. What we would do in this case is factor the denominator. And then when we factor the denominator, we get x plus 1 times x plus 4. We set that equal to 0. And then we see that x is not allowed to be -4 or -1. And so there we have, it's very easy to find the domain of a rational function. You simply take the denominator, set it equal to 0, solve for x. Whatever x values you get that are real numbers for that equation, those are excluded from the domain. All other real numbers are in the domain of the rational function. Now, let's talk a little bit about end behavior. Rational functions have behaviors at the ends, and those behaviors, a rational function may have multiple ends because there may be breaks in the rational function. Let's take an example that we're looking at here. This is the graph of 1 over x squared. And as you can see, the graph has 4 ends actually because it's broken into 2 pieces. So let's talk about a little bit of a notation here. We have x approaches a with a little plus sign at the top right hand corner. What this symbol means, this expression, this is official mathematical notation for x is going toward this x value from the right hand side. So x approaches a from the right hand side. So for example, if we look at this number 1, we see if x is approaching 1 from the right hand side, we're coming this way. And then you can see then that the y value it's approaching is 1. As x approaches 2 from the right hand side, then the y value approaches is right here, which looks like a quarter. Likewise, if the sign on the top right hand corner is a negative, then we're approaching that number from the left hand side. So over here I'll be approaching 1 from the left hand side, or I'd be approaching 2 from the left hand side, or I'd be approaching 0 from the left hand side. Then as x approaches infinity means we're going all the way to the right, and x approaches negative infinity means we're going all the way to the left. So remember that notation as we take a look at these examples here. Let's do a quick example to illustrate what we are talking about. So we have An example here, taken from the pre-calculus textbook by Blitzer. It says use a graph of the rational function in the figure shown to complete each statement, from numbers 9 to 14. So the first question is, as x approaches -3 with a little negative sign, means as x gets closer and closer to -3 from the left hand side, what does f of x go to? As we go toward -3 from the left hand side, that means we start on the left hand and approach -3 on the x-axis. We see that the graph keeps going down more and more. That means the graph is going down toward negative infinity. Negative infinity. The y value is getting lower and lower. As we go toward -3 from the right hand side, so we start on the right of -3 and let's get closer and closer, we see that the graph goes upward forever. That's positive infinity. Let's go and see what it's doing here. As x approaches 1, and this is from the left, so I look at 1, I start from the left side of 1, and I just keep going toward 1 from the left hand side. I see that the graph keeps going downward, so the y value is going toward negative infinity, sorry. And then as we go toward 1 from the right hand side, because of the plus here, I see that we start over here, we go to the right, toward 1 from the right side, the graph goes upward, so we're going toward positive infinity in this case. As x approaches negative infinity, as we see as we go more and more to the left hand side, the graph keeps getting closer and closer to 0. And as we go toward, as x approaches positive infinity, we're going toward the right hand side forever, and the graph keeps getting lower and lower till like it's going towards 0. Let me throw in a couple of additional questions here. What would we get as x approaches -1 from the left? As x approaches -1 from the left, you see that the graph, we start on the left side of -1 and we just keep going closer and closer, and you see that the graph gets closer to 0, the y value gets closer to 0. And then as x approaches that same number, -1, but from the right hand side, let's see what's happening in that case. In that case, we start on the right hand side, we just keep moving toward this. It still gets closer to 0. So we see there in this case that approaching from the left and approaching from the right gives us the same result. All right, let's get back to our PowerPoint here. Now, let's take a closer look at the graph of 1 over x squared. As you can see, when x is equal to 0, there is no value to the function. So as the x approaches 0, as the graph approaches 0, it never actually gets there, doesn't touch the y-axis. There is no y-intercept. So if we draw a vertical line at the y-axis, that's a line that the graph gets closer and closer to, but never actually touch. That's called a vertical asymptote, because it's a vertical line that the graph gets closer and closer to at one of its ends, but doesn't touch. All right. It is a sketching aid to figure out the graph of a rational function. So this is not the exact graph. It's actually not drawn to scale, but it gives you an idea of what the graph looks like. All right. So we have a vertical asymptote, because if we try to plug in 0 into the denominator, we get no answer. And when we look at the graph actually gets closer to that value, but doesn't touch it. So that indicates something very important here. We need to find out if there are any such asymptotes in a function. We call those vertical asymptotes. If we take a look at the graph of 1 over x, we have another graph with a vertical asymptote at the x-axis, at the y-axis again, at x equal to 0. So as x gets closer and closer to 0, the graph either goes all the way up or all the way down, depending on whether we're coming from the right or the left-hand side. Now, if we notice here, if we get closer and closer to 0 from the right-hand side, I plug in numbers. I plug in 1 over 10, I get 10. When I plug in 1 over 100, I get 100. If I plug in 1 over 1,000, I get 1,000. So you see that as we get closer and closer to 0, right-hand side, the answers get bigger and bigger. If I try going closer and closer to 0 from the left-hand side, -1 over 10, then -1 over 100, you'll see that the graph still gets the answers still get bigger and bigger, but now they're all negative. So the graph goes downward to negative infinity. So does the graph have an x-intercept? Well, if I plug in 0 for, if I set the function equal to 0 and solve for x, I will get no answer. So in that case, we have what we call a horizontal asymptote. A horizontal asymptote. And the graph will never cross the function at a horizontal asymptote, at least not as it ends. Now, how do you know if you'll have a horizontal asymptote? What happens is as x goes further and further to the right or further and further to the left, the graph settles down near to some value. Not always 0. Sometimes it's other numbers. So let's take a quick look at some examples here and see what we can do with those. All right. Oh, yes. My apologies. I have to illustrate something else first. So let's go back to the video. When we're doing the graphing of a function, we'll go back to the transform the asymptotes in a minute. But I just want to point out the transformation of a function. If you start out with one of those basic graphs like 1 over x over 1 over x squared, the transformation rules about transformations of functions apply. So for example, if I'm adding 3 plus 1 over x, that means I'm adding 3 to all the y values. That shifts the graph up 3 units. And so this blue graph is now the new graph. The brown, yellowish, goldish graph was the original 1 over x graph, and then we add 3 and it moves everything up. The vertical asymptote gets shifted up, which makes it the same line. The horizontal asymptote gets shifted up, which moves it from 0, from y equals 0 to y equal to 3. So let's now go back to our examples that I was going to talk about here. So the function, this again is from the Blitzer section 2.6. In exercise 45 to 56, use transformations of f of x equal to 1 over x and f of x equal to 1 over x squared to graph the rational function. Now, in this case, since we're adding to the x's in the denominator, our graph or parent graph here, our parent function, fxn is short for function, our parent function is y equal to 1 over x. And then what we're doing is replacing the x with x plus 2, and then we're subtracting 2 from the whole thing. So what we're going to do is shift the graph left 2 units because of x plus 2, and then we're going to shift the graph also up, sorry, not up, down 2 units because we're subtracting from the y values. So what we will then do is draw our graph. I'm going to draw the original function, kind of a rough sketch of the original function, so we can see what it looks like. And then I'm going to shift this graph to the left 2 units and down 2 units. So what that will do now is create for me 2 different asymptotes. The original asymptotes were the y-axis and the x-axis. The y-axis has equation x equal to 0, and the x-axis has equation x equal to the x-axis equation y equal to 0. So when I shift the graph over now, what I will end up with is my asymptotes. My y-axis gets shifted over to the right, to the left 2 units, and the x-axis gets shifted down 2 units. So my new asymptotes are x equal to y equals to -2 and x is equal to -2. When I draw the graph now, the graph gets shifted to the left and down and to the right and up. Oh, apologies, drew it the wrong place. So this blue graph is what the new graph looks like. And again, it's a little bit messed up, not drawn very smoothly, but you get the idea of what I'm trying to do here. Let's go on to this graph here. In this case, the parent function is the graph y equals to 1 over x squared. And all we're doing here is shift the graph downward 4 units. So once again, we start off with the graph of our original function. I'm going to use those as my asymptotes. So, pardon me, let me just do a couple more here. And then do a little adjustment. So the original function, the graph of 1 over x squared, looks basically like this. Again, not drawn to scale. Then this says shift the graph downward 4 units. So now what happens is the vertical asymptote is the y-axis. The horizontal asymptote is shifted downward 4 units. So the whole graph gets shifted downward 4 units. And so the graph looks something like this. Not exactly drawn to scale, but you get the idea. And the line y equal to 4 to negative 4 is the horizontal asymptote, and the y-axis is still the vertical asymptote. That's that. Now let's take a quick look at number 56. Parent function here. The parent function is y, again, is equal to 1 over x squared. In this case, we're shifting the graph to the right 3 units. I'll write that in caps. And we're shifting the graph up 2 units. So, once again, I will draw my grid. All right, so we start out with our original function, which is like it is over here. I drew the grid a little differently, but it's the same graph. And that was a general idea of what the original function looks like. Since we shift the graph to the right 2 units, then the 3 units, then the vertical asymptote is going to be shifted as well. The horizontal asymptote in that case will stay the same, because shifting the horizontal line to the left or right will keep it the same line. And then this says shift the graph up 2 units. So now my vertical asymptote, my horizontal asymptote, is now going to be up 2 units. So something like that. Now what that does is that means the graph is now going to be shifted over to the right 3 units and up 2 units. And that's what the graph looks like. And again, my asymptotes were shifted to be x equal to 3 and y equals to 2. And that is an illustration of what we're dealing with here. Let's continue with the rest of the PowerPoint. So how do we find vertical asymptotes? To find vertical asymptotes is pretty easy. You set your denominator equal to 0 and solve for x. Now there's a little stipulation here. What you want to do is factor the numerator and denominator if possible. If the numerator cannot be factored, like in this case, then that's fine. When we factor the denominator here, we get x minus 4, x plus 1. So those are the places where the vertical asymptote would occur. Now what we do, once we find those domain restrictions, what we do is plug them into the numerator to see if that causes the numerator to be 0 as well. If that doesn't cause the numerator to be 0 as well, then x equal to that number is a vertical asymptote. So when I plug in -1 here, I get 1 minus 2 plus 5. That is not 0. So x equal to -1 is a vertical asymptote. When I plug in 4 into the function here, I get 4 squared plus 8 plus 5. That is not going to be 0. So x equal to 4 is also a vertical asymptote. So the two vertical asymptotes for this graph would be x equal to -1 and x equal to 4. And I've just put this here to remind us of what the original function was. Now, as a general rule then, how do you find vertical asymptotes? Very simple. You first find the domain restrictions, and you find where to find the domain restriction, you simply set the denominator equal to 0 and solve for x. All right, then what we would then do is factor the polynomial and cancel common factors, and then see which of the remaining factors of the denominator is there. Whichever remaining factor gives you 0, x equal to that number is the vertical asymptote. So when you factor completely, you take the linear factors and set them equal to 0 in the denominator. You cancel what can be canceled first, set the linear factors equal to 0, and then see what x is in that case. That x value should not also give you 0 for the numerator, so x equal to that number is a vertical asymptote. And you can see here a few graphs of vertical asymptote. As x approaches a from the right, the y goes to positive infinity. As x approaches a from the left, the graph goes to positive infinity. As x approaches a from the right, the graph f goes to negative infinity. And as x approaches a from the left, the graph goes to negative infinity. So in a vertical asymptote situation, as x gets closer and closer to a finite real number, the y value goes up to positive infinity or to negative infinity. Let's take a look at a few examples here. So in this case, we're going to find the vertical asymptotes, and that's it. All we're going to do is find the vertical asymptotes. So let's go through the process here. First, we're going to find the domain restrictions. And actually, I'm going to factor and then define the domain restrictions. So I factor first, numerator and denominator. F of x is equal to x over x minus 1 times x plus 1. And as you can see, there's no common factor that cancels in the numerator and denominator, which is fine. So the domain restrictions now. So the domain restriction is whatever makes the denominator equal to 0. So we have x minus 1 times x plus 1 equal to 0. So that gives us x is equal to -1 or +1. Now if I do f of any of those numbers, f of -1 will not give me, if I plug in 1 into the numerator or -1 into the numerator, you will not get 0. And since the denominator doesn't give you 0, Um, since the numerator doesn't give you 0, then we know that x equal to -1 and x equal to +1 are the vertical asymptotes. And that's that. Now let's take a look at the next example here. The next example, we have the same denominator. However, the numerator now is not x. The numerator is x minus 1. So I'm going to go through the process again. G of x is equal to, and I'm going to factor the numerator and the denominator. The numerator can't be factored, so I leave it as that. And I see that the domain restriction is the same. We set the denominator equal to 0, and we're saying x, whatever x values work, we throw those out. So I'm going to say not equal to 0. The bottom cannot be equal to 0. So that means x cannot be -1 or +1. Now, to find the domain, to simplify this, what I realize is I take the function and I cancel what can be canceled after factoring. Now, that doesn't take this number out of the domain restriction. The function still doesn't work when x is not equal to 1, when x is equal to 1. But now it's a simplified function. It is 1 over x plus 1, where x is not positive or -1. X is not still allowed to be positive or -1. So the vertical asymptote is only occurring at x equal to -1, because that's the only place when you simplify the function, that's what give the domain restriction will give you here, even though we still remind ourselves that -1 still doesn't work. What that means is the graph really just has a hole at 1, not a vertical asymptote. So if I were to draw this graph, in reality, it will just be a transformation of the graph of 1 over x with an additional restriction that there's a hole where x is equal to 1. So if I were to draw this graph, it would be a transformation of the graph of 1 over x by shifting it to the right, and then I would put a hole where x is equal to 1. So the graph will look something like this. And I said shift it to the right, it's actually shifted to the left. And then where I have 1, I'll have a hole, and the graph will continue. So that's at x equal to 1. And this is the graph, as the line x equal to -1. That's our asymptote. And that's what the graph looks like. Now let's take a look at this third example. In this case, we have x minus 1 over x squared plus 1. And if you try to factor x squared plus 1, it does not factor. In fact, what we're going to do is we're going to set the denominator equal to 0 and solve for x and see if we get any domain restrictions. So once again, we're going to talk about our domain restrictions here. And we say x squared plus 1, which is our denominator, equal to 0, which means x squared would have to be equal to -1. This does not give us any real number solutions. A real number doesn't square to give you a negative. So this is no real number solution. So if there's no real number that causes the denominator to be equal to 0, then there are no domain restrictions here. No domain restrictions. No domain restriction. And so if there's no domain restriction, so the domain then is all real numbers. The domain is negative infinity to infinity. And since the domain is negative infinity to infinity, then there is no vertical asymptote because there's no place where the graph breaks horizontally. No vertical asymptote. And there you have it. Now let's go back to the PowerPoint and talk about horizontal asymptotes. So a horizontal asymptote is a horizontal line y equal to b that the graph approaches as x approaches positive or negative infinity. So as we go further and further to the right or further and further to the left. It turns out that for rational functions, each rational function will only have one horizontal asymptote if it has any at all. So whether you go to the right or to the left hand side, you will get the same horizontal asymptote. That's particularly for rational functions. So how do we find horizontal asymptotes for rational functions? Pretty simply, we look at the degree of the numerator and the degree of the denominator. If the degree of the numerator is smaller than the degree of the denominator, then the horizontal asymptote is the x-axis. In other words, the line y equal to 0. So if the degree of the numerator is less than the degree of the denominator, then the x-axis is the horizontal asymptote. That is the line y equal to 0. So let's take a look at this example here. The degree of the top is 1 because that's a linear expression, and the degree of the bottom is 2. That's a quadratic expression. Since the degree of the top is less than the degree of the bottom, then we have a horizontal asymptote. And the reason for that is as we go further and further to the right or to the left, the only values that really matter are the highest values, the x and the 2x and the x squared. As you notice, the bottom would be getting bigger more quickly than the top. So that limits your results to 0. The values get closer and closer to 0 because the top is continually getting smaller than the bottom. So the x-axis will be our horizontal asymptote, or x-axis will be our horizontal asymptote. That is if the degree of the top is smaller than the degree of the bottom. The degree of the numerator is smaller than the degree of the denominator. If, however, the two functions have the same degree, if the degree of the numerator is equal to the degree of the denominator, as the numbers get bigger, either to the left or to the right, the only thing that will matter is the leading term, and the x squares would eventually cancel in this case, leaving only the numerator coefficient divided by the denominator coefficient. So to find the horizontal asymptote, if the degree of the numerator is the same as the degree of the denominator, you simply divide the leading coefficients. Leading coefficient of the numerator divided by leading coefficient of the denominator. In this example, the degree of the numerator and the denominator are both 2. So the horizontal asymptote is simply the line y equals to 2 over 1. 2 over 1. Leading coefficient of the top over leading coefficient of the bottom if the degrees are the same. Simplifying, we get y equal to 2. So the horizontal asymptote here is the line y equals to 2. Now, if the degree of the numerator is smaller than the degree of the denominator, then there will be no horizontal asymptotes. There will be no horizontal asymptotes. However, there's an additional possibility of another type of asymptote called an oblique asymptote, or a slanted asymptote, a slant asymptote. And that occurs if the degree of the top is 1 more than the degree of the bottom. The degree of the top is 1 greater than the degree of the bottom. So the degree of the top here is 3, the degree of the bottom here is 2. And if we factor and simplify and there's no cancellation, basically what we have here is long division. We do the long division. We get x plus 5 plus a remainder, and the remainder is a constant. That expression there, x plus 5, indicates the oblique asymptote. It's a slanted straight line. So the equation y equal to x plus 5 is the oblique or slant asymptote. That occurs if there is no horizontal asymptote and the degree of the top is 1 more than the degree of the bottom. If the degree of the top is more than 1 greater than the degree of the bottom, then there's no oblique asymptote either. So in which case there will be neither horizontal nor oblique asymptotes. So as a general summary, let's take a look at what we said here. If you have a rational function in standard form, leading polynomial on top, polynomial at the bottom, if the degree of the top is less than the degree of the bottom, then the line y equals 0, which is the x-axis, is your horizontal asymptote. If the degrees are the same, then the horizontal asymptote is y equal to the quotient of the leading coefficients, top leading coefficient divided by bottom leading coefficient. If the degree of the numerator is bigger than the degree of the degree of the denominator, then there is no horizontal asymptote. Please note that if there is a horizontal asymptote, then there will not be an oblique or slant asymptote. However, if there is no horizontal asymptote, you might want to check for an oblique asymptote. So how do you check? Well, if the graph of a rational function has a slant or oblique asymptote, if the degree of the numerator is 1 more than the degree of the denominator. So in general, if they have no common factors and the degree of the top is 1 more than the degree of the bottom, and the bottom is we're not talking about a straight line here, so it's not like a linear function over a constant. That's just a straight line. But if we're talking about a degree 2 or more polynomial over a degree 1 or more polynomial, then we are talking about an oblique asymptote in simplified form. To find the oblique asymptote, you simply do division, whether long division or synthetic division, whichever is appropriate, and you look at the quotient. That should be a straight line, a linear expression. So y equal to that expression is the oblique asymptote. So let's take a look at this example here. Pardon me a minute. Let's take a look at the example I just mentioned here. There we go. So the first we're going to do is we're going to try to find our domain restrictions. So, yeah, I'm going to try to factor the top. Apologize for that. Now, when I try to factor the top, if I look at the discriminant, it will tell me if I can factor or not. So the discriminant of the top is b squared minus 4ac. In this case, because it's quadratic, that's equal to negative 5 squared minus 4 times 2 times 7. And that's 25 minus 56, which is going to be equal to negative 31. That does not factor because the discriminant is negative. So we now know that this function, we know that the vertical asymptote is x equal to 2. See, and then we say now, and so let me just put a little note here. Note that x equal to 2 is a vertical asymptote. It's the only one actually for this function. Next, since the degree of the top, the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. And now we also notice that the degree of the top is 1 more than the degree of the denominator. So I'm going to do a little synthetic division here. I set this equal to 0 and solve for x. I get x equal to 2. I put my coefficients, 2, negative 5, and 7. draw a horizontal line. I drop the leading coefficient down, so I end up with 2, and then 2 times 2 is 4, which I will then add to the -5. -5 plus 4 is -1. 2 times -1 is -2, and then I will add that to 7. I get 5. So the expression then can be written as 2x minus 1 plus 5 over x minus 2. This here is what tells me my oblique asymptote. So the oblique asymptote is y equals to 2x plus 1, which is the quotient after we do division, either long division or synthetic division. So generally speaking, if you want to find out how to find asymptotes, to find vertical asymptotes, you find the domain restrictions and you simplify the rational expression if possible, and then you check the domain restrictions. Make sure whatever causes the denominator to be 0 doesn't make the numerator 0 as well. If that happens, if you find numbers that makes the denominator equal to 0 and the numerator not equal to 0, then x equal to that number is a vertical asymptote. To find horizontal asymptotes, you check the degrees. If the degree of the top is less than the degree of the bottom, then the x-axis is a horizontal asymptote, which is equation y equal to 0. If the degrees are the same, the degree of the top and the degree of the denominator are the same, then the horizontal asymptote is equal to y equal to the quotient of the leading coefficients. Top leading coefficient divided by the bottom leading coefficient. If the degree of the top is greater than the degree of the bottom, then there is no horizontal asymptote. If the degree of the numerator is 1 more than the degree of the denominator, then you find the oblique asymptote by doing long division. And now let's do a few quick examples here, and that will then we'll move on to the last part of our lesson. So first of all, in this case, to find the horizontal asymptote, it's a linear expression over linear expression, and they do not cancel. So I just set the denominator equal to 0 and solve for x. In actuality, the domain restriction would be x equal to 0. So the vertical asymptote is x equal to 6. All right. And of course, when we plug that into the numerator, we're quite fine. We have no problems here. Now, if you notice now, the degree of the numerator is 1 and the degree of the denominator is 1. So what does that tell us about our horizontal asymptote? We simply divide the leading coefficients. So what I'm going to do a little writing here. I'm going to say, since the degree of, I'm going to write the degree of the numerator in a weird way. I'm going to write degree numerator equals degree denominator, just for shorthand. So what I'm saying here is the degree of the numerator is equal to the degree of the denominator. Since that occurs, then our horizontal asymptote is found by dividing the leading coefficient. So I'm going to divide y equals to leading coefficient 3 divided by 1. So our horizontal asymptote is just y equals to 1. Now, since we have an horizontal asymptote, there is no oblique asymptote. So since there is a horizontal asymptote, then no oblique or slant asymptote. And that's that. Let's go on to this one here. To find the horizontal asymptote for this example, what we're going to do is factor the numerator and denominator. So we have h of x is equal to x minus 2. That's a difference of cubes, so it's x squared plus 4x, not 4x, plus 2x plus 4. And then the denominator, it's a simple quadratic, x minus 2 times x plus 3. Apologies, x minus 3. And then I can cancel the common factor, and now I see that the vertical asymptote is simply x equal to 3. We still have the domain restriction that x is not allowed to be equal to 2 or 3, but the only one that gives us an asymptote is x equal to 3, and that's that, because the x minus 2 canceled in the numerator and the denominator. Now, if I take a look at this expression, the simplified expression, I realize that the degree of the top is bigger than the degree of the bottom. So since the degree of the numerator is less than the degree of the denominator, then there is no horizontal asymptote. And now for the oblique and slant. If you look at the simplified expression here, we have the degree of the top is 1 more than the degree of the bottom. And please note again, I'm looking at the simplified expression, because when I look at the simplified expression, it will give me a better information and even make it easier for me to divide. And I'll remind myself that 2 and 3 are still not allowed to be used in this function. So I use 3 as my divisor, and I do a little synthetic division here, and then go through the process. And I only need the quotient, so I put down the 1. 3 times 1 is 3. I get 5. 3 times 5 is 15, and I get 19. And all I need actually is this part of the expression. And so the oblique asymptote here is y equals to 1x plus 5. I don't care about the remainder. That's the remainder. I don't need that for my I do not need that for my oblique asymptote. And so that's what we have for that one. Now let's go on to this guy here. In this case, I'm going to write the expression in terms in simplified form. The top is just one term, and the bottom can be factored to be x squared plus 1 times x squared minus 1, and x squared minus 1 factors to be x plus 1, x minus 1. So if you try to do the domain restriction now, you will realize that the only parts that give you 0 in the denominator are 1 and negative 1, and those numbers do not give you 0 in the numerator. So our vertical asymptotes are x equal to -1 and x equal to +1. Those are my vertical asymptotes. Now let's take a look at the horizontal asymptotes. The numerator of the numerator is degree of the numerator is less than the degree of the denominator, as you can see. So since the degree of the numerator is less than degree of the denominator, then y equal 0 is the horizontal asymptote. In other words, the x-axis is the horizontal asymptote. Now, as before, if there is a horizontal asymptote, then there cannot be a oblique asymptote. So since there is a horizontal asymptote, then no oblique asymptote is present. And there you have that. We'll do 3 more examples, and that will be that for this part of the concept, and then we'll talk about graphing. So in this case, we have a little bit more complicated looking expressions. What you want to do is factor what can be factored first. So I'm not going to go through the process of showing the factoring just for the sake of time. I'm just going to go right into the result of factoring, and I'm going to leave you to figure out the factoring, because that's just an earlier concept. The numerator here factors to be x minus 4 times 2x plus 3. And the denominator factors to be x minus 4 times 3x plus 1. So when you factor that, you realize that that cancels. And if that cancels, that leaves us with this expression here. I'm going to simplify it a little bit more before I write my vertical asymptotes. So q of x is actually 2x plus 3 over 3x plus 1, with the stipulation that x is not equal to either 4 or negative 1/3. And therein we get our vertical asymptote. Is the bottom part that is left that wasn't cancelled. So the vertical asymptote is x equal to negative 1/3. Now again, since the degree of the top is equal to the degree of the bottom, so the horizontal asymptote is just y equals to leading coefficient divided by leading coefficient. And again, in this case, since there is a horizontal asymptote, then there is no oblique asymptote. So, all right, now that it's back, we can now say that there is no oblique asymptote since there's a horizontal asymptote. Now let's take a look at the next example here. What we're going to do is factor the polynomial again. If possible, turns out the numerator factors to be 2x plus 7 multiplied by 4x minus 1. And the denominator is not factorable, it's just a linear expression, so I just put it in parentheses. And it turns out that the whole denominator gets cancelled. What that means is the function is really r of x equals to 2x plus 7 as long as x is not equal to 1/4. And since that there's no denominator to cause a problem, then there is no vertical asymptote. Basically what this is a straight line with a hole at 1/4. So there is no horizontal asymptote either, and there is no oblique asymptote. All this is, and I'll type that in right now, all we're dealing with here is a straight line with a hole at x equal to -1/4. This is a straight line with a hole at x equal to not -1/4, sorry, 1/4. All right. So as a result, then there is no horizontal asymptote, and there is no oblique asymptote, and there's no vertical asymptote either. So let's take a look at the last example here. All right, so let's take a look at this last example here. We are going to factor this quadratic expression, g of this rational expression. The numerator factors to be x minus 1 times x plus 1 times x squared plus 2 plus 1. And the denominator factors to be x times x minus 1. As we can see, x minus 1 is a common factor. So when I rewrite the expression, I get x plus 1 times x squared plus 1 over x, with this condition that x is not either 0 or 1. Now, as you can see here, pretty clearly, the vertical asymptote is x equal to 0. And again, the degree of the top is different from the degree, is greater than the degree of the bottom. So there is no horizontal asymptote, because the degree of the numerator is greater than the degree of the denominator. Now, if we take a look at this, the degree of the numerator is more than 1 unit greater than the degree of the denominator. So there's not going to be a slant asymptote either. Since the degree of the numerator is more than 1 unit greater than the degree of the denominator, then there is no oblique or slant asymptote. The degree of the numerator was 2 units more than the degree of the denominator, so there will be no oblique or slant asymptote. And there we have it. So what we're going to do now is we're going to go on to the graphing of rational functions, and that will be that for the lesson. Okay, now finally, we're going to talk about graphing rational functions. Graphing rational functions. And when we're graphing rational functions, we want to bear a few things in mind. Shauna Hader puts it nicely in this series of steps. You want to identify the domain, and the domain excluded values will also indicate where your vertical asymptotes are likely to be. You want to identify your y-intercept if there is one by just substituting 0 for x. You want to find your x-intercepts by setting y equal to 0 and solving for x, in which case it would be the numerator that you would solve for x, because the denominator would not cause a function to be equal to 0. You want to test for symmetry by replacing your x's with negative x and then seeing if you get the same expression or the negative of the original expression. In other words, whether the function is odd, even, or neither. That is not absolutely necessary, but it's very helpful. You want to check for horizontal and oblique asymptotes by checking the degrees of the numerator and the denominator and doing division as necessary. And then you want to plot some additional points on either side of the vertical asymptotes to get an idea of where the graph is going to go through. Then you'll join those points using a smooth curve. So let's take this example. We have 6 over x squared minus x minus 6. We're going to set the denominator equal to 0 and solve for x, and we see that the domain restrictions are x cannot be -2 and x cannot be 3. So, and then since there's the numerator has no x's, then we know that those will be our vertical asymptotes. Now we know the vertical asymptotes. Then we're going to find our y-intercepts by plugging 0 for x. When we plug in 0 for x, we get 6 over -6, which is y equal to -1. So we know the graph crosses the y-axis at the point -1, 0, -1. So now we have two vertical asymptotes and the y-intercept. If we try to find an x-intercept, we set the fraction equal to 0, but that would mean 6 would equal to 0, and that is not possible in the real plane. So therefore, we see that there will not be any x-intercepts. If we replace x with -x, we will end up with a different expression than we had before, totally different. So it's not equal to the original, nor is it the negative of the original. So there is no symmetry. This is neither an odd or not even function. Now let's take a quick look at horizontal asymptote. Since the degree of the top is 0, it's a constant, and the degree of the bottom is 2, then the degree of the top is smaller than the degree of the bottom. So the horizontal asymptote is y equal to 0. And so we are saying that the horizontal asymptote is the x-axis. So that's what the graph approaches as we approach negative or positive infinity. Since there is a horizontal asymptote, there is no oblique asymptote. So we have all our asymptotes now. We have a horizontal asymptote, y equals 0, which is the x-axis. Two vertical asymptotes, x equal to -2 and x equal to 3. And we have the y-intercept at -1. Now let's plot some additional points. So since we have a vertical asymptote here, let's plot some points on the left side of that. -4 gives you approximately 0.4. And then we can plot a few more points there, which show some additional points between. So we plot 1, and that will give us -1. And then we choose some additional points on the other side. We plot 4, we get 1. And in reality, you should be plotting a lot more points than indicated here. So once you plot those points, we connect them as best we can. And that was going to be what the graph kind of looks like. It's not an absolutely neat graph, but it is a reasonable representation. I would recommend that you plot at least 3 additional points on the left. So if you put 4 points on the left side, 4 points in between, and 4 points on the right side of the vertical asymptotes, that should give you a reasonable representation of what the graph looks like. And this is what it actually looks like on a graphing calculator. All right. The graphing calculator doesn't always show the vertical or horizontal asymptotes, by the way. So let's try another example here. The domain restrictions for this one is x is not equal to 3 or -3. As you can see, we set the denominator equal to 0 and solve. But if you factor the numerator and denominator, you'll see that x plus 3 cancels. So the vertical asymptote only occurs for this factor x minus 3. So the only vertical asymptote is actually at x equal to 3. Not at x equal to -3, because that is just going to be a hole in the graph. So we only have one vertical asymptote. And what we've done here is we've written the simplified version of this graph. But remember that x is not allowed to be -3 nor 3. Now let's see if we have a y-intercept. I plug in 0 for x, I get -1/3. So the graph crosses the y-axis at -1/3. Then we're looking for x-intercepts. I plug in, I set the expression equal to 0. So for x, I see that x equals to -1 is an x-intercept. Then we're going to look for in a horizontal asymptotes. The degree of the top and the degree of the bottom are the same. Oh, we have check for symmetry. There is no symmetry again in this case, because when we plug in -x for x, we do not get the same expression nor the negative of the original expression. To get horizontal asymptotes, we see that the degree of the numerator and the degree of the denominator are exactly the same. So the horizontal asymptote is just y equal to the leading coefficients divided by each other. Top divided by bottom. So we get y equal to 1. So that's a horizontal asymptote right there. And what it turns out is that this expression is actually a transformation of the graph of 1 over x. If you split it into parts, well, it may be a little hard to see, but it's actually the graph. The graph is actually 1 minus 4 over x minus 3. So it's going to be a little weird. It's going to be reflected over the x-axis and then shifted to the right 3 units and stretched by a factor of 4. So in any case, we just plot the points. We plot multiple points on either side of the asymptote. I recommend plotting multiple points, not just 2 or 3 points. And then once you have enough points, you just join them with a smooth curve, and there you have it. That's an approximate look at what the graph is looks like. So I'd like to remind you, though, that when we simplified the expression, we also remembered that the domain restriction was not only at 3, but at -3. So you should not have a point at -3. Now, in the simplified expression, if we were to substitute -3 into the simplified expression, the answer would have been 1/3. But remember, in the original expression, there was not supposed to be a value for -3. So what we do is put a hole at -3, 1/3, and that would be what indicating that there was a domain restriction. Vertical asymptote at 3, hole at -3, with where the graph would have had a value of 1/3. And so you can draw it on your calculator. If you notice, the calculator actually doesn't indicate the hole. So the calculator doesn't. In this case, the calculator drew the vertical asymptote, but it did not indicate the hole. So you need to be careful of this when you're drawing these on the calculator. The calculators do not indicate holes, and they only sometimes indicate vertical asymptotes. And you notice that also that the horizontal asymptote isn't indicated either. So you cannot simply rely on the graphing calculator to give you the information. That's all for this lesson. I recommend that you look at Khan Academy videos and exercises, as well as openstax.org, openstax.org. They have free math textbooks, including college algebra textbooks and practice exercises. They also have an Android app, OpenStax. Just search that in your Android. It's a free app with free textbooks for other subjects, but particularly in this case, college algebra. All the best, keep practicing, and keep succeeding.